Okay, please.
Okay, thank you very much for the introduction. So before starting, I would like to acknowledge Dennis Sip and Tim Colonius for their contribution in this work. So what I will be discussing today will be along the lines of the previous talks, and specifically the input-output analysis that Mihailo showed, but we're going to extend it to the full nonlinear regime, and also the minimal seed concepts that we saw earlier. But now we're going to think of the minimal seed as an expression of it in the frequency domain. So we're going to tackle it from a frequency domain approach. And of course, we're interested also in transition mechanisms of incompressible boundary layers. We will be examining the simplest case, a flat plate, three-dimensional. And we will, throughout this talk, we will have an objective definition of transition, which will be the overshoot of the skin friction coefficient from the laminar Blasius values all the way to the turbulent regimes. And here you see a really expensive DNS calculation performed by Tara and Sayadi. And one of the objectives of this work is actually, instead of using the fully resolved DNS, to come up and develop a tool that interpolates optimally between linear methods and fully resolved DNS. We will use a method called harmonic balance to achieve that. And once we have this computationally efficient tool, we will be able to answer questions like what is the worst case path to transition from a frequency domain perspective, complementing the already existing methods about optimal disturbances in the time domain. And why we will be using a frequency domain approach? Because we strongly believe that the interpretability of the transition mechanisms is more intuitive. As I said, is a complementary problem to solving optimal initial disturbances. And for the flat plate boundary layer, there is a variety of mechanisms actually that has been proposed that can cause transition, like K-type or H-type of transition, combining multiple waves that they resonate. There are also other types of mechanisms like oblique transition, exactly like Mihailo showed earlier, that they combine both nonlinear interactions and also non-modal transient growth through the lift-up mechanism that leads to the generation of streaks and then subsequently to their breakdown. This is exactly when the skin friction coefficient reaches the fully turbulent regimes. So, and the motivation when I started this study actually was, if someone would ask you the question, what is the worst case mechanism out of all these? Actually, I had no idea. Probably some of you may have knew, but I really didn't know. And secondly, I wanted to let the optimization actually find out of all the possible mechanisms, what is the optimal mechanism for transition in the frequency domain. So what I'm going to tell you today, I will recap some results just to get a background about the linear mechanisms for a flat plate incompressible boundary layer. We will use a resolvent type of analysis. And the two novel parts will be actually solving the harmonic-balanced Navier-Stokes equations in the frequency domain for finite amplitude perturbations, since we want to predict transition. And secondly, I will introduce also nonlinear optimization. So I will solve exactly the same problem for the minimal seed, but now in the frequency domain using nonlinear optimization. Most of my slides is a repetition of what the previous author said. And actually, if someone looks at the global linearized Navier-Stokes operator, we'll see that all the eigenvalues are stable. So actually, for subcritically transitioning flows like the boundary layer, we need another formulation. We need to introduce a forcing F on the right-hand side of the linearized Navier-Stokes equations that actually communicates with the response through the resolvent operator. And optimization involves solving a singular value decomposition of this operator to find the optimal amplification mechanisms, as was described in all the previous talks. I will be using a volumetric forcing, but actually one of the novelties here is that my volumetric forcing will have an arbitrary number of harmonics, both in the beta, in the z direction, and I will have an associated wave number beta, and also an arbitrary number of n harmonics in omega, so it creates an n periodic flow. The response, governed by the nonlinear Navier-Stokes equations now, will be also multi-harmonic and without loss of any generality, we will assume that at least it responds to these frequencies of the forcing. And as I said earlier, in a linear framework, the two methods are absolutely complementary. And this has been shown already. I can solve the resolvent problem, so finding optimal volumetric forcings that excite the energy of my flow, or I can solve an optimal transient energy growth problem. So at a finite time t, I calculate what is the optimal initial condition that leads to the maximum energy at this finite time t. This has been tackled as well by the group of Dan Henningson more than 10 years ago. And actually, as I said, both time domain and frequency domain give same results. So in a frequency response interpretation, we believe that this one is easier to understand, because if I go on my beta omega gain plot, I will see two structures that can achieve maximum amplification. At 0 omega, I have streaks, and I have oblique waves, actually it's oblique TS waves, seen due to the presence of the lift mechanism. So two well-known mechanisms, and that we saw on the right-hand side. So these time domain methods over the last years, they were also extended in the nonlinear regime. So instead of optimizing for finite, the linearized Navier-Stokes equations for finite perturbations, we use the nonlinear Navier-Stokes equations, and we ask the question, what is the minimal seed? But as you can see, these methods in the frequency domain on the right-hand side, they were not extended in the nonlinear regime. And actually, this is what we did, and all the details are in a recent published paper in JFM with Tim and Denis. I'm going to avoid calling it nonlinear resolvent operator, because the resolvent is a linear operator by definition, and I will use the expression nonlinear input-output analysis. So I will try now to find optimal multi-harmonic forcings governed by the nonlinear Navier-Stokes equation that maximize in an optimal sense the objective function for my transition, which is the skin friction coefficient. So I will do two things. I will introduce this interpolant, as I call it, that interpolates between linear methods and fully resolved DNS in the frequency domain. We call it Harmonic-Balanced Navier-Stokes. And then, having this computationally efficient tool, I will calculate the optimal nonlinear dynamics leading to transition. And there were many other attempts as well that actually people have used to extend these linear methods to the nonlinear regime, like a weakly nonlinear analysis, as Mihailo showed earlier. Actually, we did some of this analysis for the boundary layer, and we had some issues. And this is when we came across the self-consistent or the quasi-linear approach. For the cylinder flow, it was really well demonstrated by Galler and his colleagues a few years ago. So the trick she did is like having a coupled system of a mean flow and linearized perturbation equations that they talk to each other through the modifications of the Reynolds stresses at the perturbation level. Okay, so we solve a linearized perturbation equations. These ones, they feed back as a forcing term in the base flow or the mean flow equation, and we can reach a self-consistent solution of these equations. We have two equations with two unknowns, the mean flow and the perturbation. So now imagine that instead of having just one harmonic, I have n number of harmonics in that formulation, but also m number of harmonics in the span-wise direction. So we're going to do this exactly a bit systematically. So we will start with the Navier-Stokes equations, retaining the nonlinear terms, and I will introduce a Fourier expansion in there, keeping an arbitrary number of both harmonics in omega and in span-wise direction z. I will introduce this expansion in the Navier-Stokes equations, and I will do what is called the harmonic balance. Actually, is another way to call it is like Fourier-Galerkin expansion. So this gives me a set of coupled equations that non-linearly talk to each other depending on the number of truncated frequencies. So this equation is a bit difficult to understand. So I will show you just a few examples now how this works. And let's assume that I'm only in the time domain. I have my mean flow equation on the top. On the bottom is the linearized Navier-Stokes equations. And I have also for this case a forcing on the right-hand side. So the interaction of the wave 0, 1 with itself, it will create a mean flow modification. And this one is a self-consistent system that I can easily solve. So what happens if I introduce a second harmonic? So I will not assume that my second harmonic due to the nonlinear response is weak, but I will try to resolve it, okay? So now you can see that due to the triadic interactions, the first harmonic interacts with itself and creates a forcing at 2 omega level. The second harmonic with a complex conjugate of the first one causes a forcing at 1 omega. And then they have two nonlinear interactions from the self-interaction of 1 omega and 2 omega back to the mean flow. Again, 3 equations for 3 unknowns. And in that case, I don't have to specify the base flow, the mean flow, and the perturbations at these two frequencies are a self-consistent solution of these equations. And as I said, we can generalize that to an arbitrary number of n harmonics using a Fourier-Galerkin method. But now we can play exactly the same game in the span-wise direction. Exactly what we did with the frequencies, we can do it with the span-wise wave numbers. So in that case, now at the linear level, I have 3 equations, 3 linear equations that can be either a steady 3D wave or a planar unsteady wave or an oblique 3-dimensional wave. At a linear level, if I keep only one harmonic at each direction, I get a self-consistent quasi-linear system that I can easily solve. Things become a bit more complicated if I introduce more harmonics. So I cannot write the example here. For the case that I have 2 harmonics in each direction, I will have 9 equations that I have to solve and many triadic interactions. I will use a compact formulation now, R equal F for the nonlinear harmonic balanced equation. I have truncated them and I solve them with a Newton method. This is a nonlinear system of equations that I can get an analytical expression for my Jacobian. So to calculate the correction due to the Newton step, these linearized equations is actually solving multiple resolvent problems or multiple linearized Navier-Stokes equations simultaneously. We came up with a really smart way due to the block structure of these equations that are diagonally actually dominant to invert this system and solve it using a block Jacobi and a GMRS iterative method. So we avoid doing a global LU decomposition of this operator. We validated the method assuming a specific forcing for K-type transition. And actually now we can get this kind of responses only using just a few harmonic components. So here I'm showing results only with, I think, 2 or 3 harmonic components in time and in space, and we get all the stages associated with K-type of transition. And now I come to the interesting part, which is, I don't know what is the optimal transition mechanism, and I will use nonlinear optimization to answer this question. So what I will do, I will set the following optimization problem. I will ask the question, what is the optimal forcing F, multi-harmonic, with a finite amplitude alpha, constrained now by my harmonic-balanced Navier-Stokes equations, instead of the expensive DNS, that gives maximum shear stress, or maximum drag, or maximizes the dissipation. And I will use a typical adjoint looping, solving the forward nonlinear problem, the harmonic-balanced Navier-Stokes, the adjoint, and I will update the solution using a steepest ascent method. Because this optimization is quite cheap, I can perform that over a range of fundamental frequencies. So I have chosen the truncation to be only 2 harmonics in omega, 2 in beta, and I change the fundamental omega 100 times approximately to scan all the possible fundamental omega and possible omega beta values. So this is the first interesting plot that we had, that the nonlinear optimal mechanism actually is focused only on the oblique waves, okay? And probably after Mikhailo's talk as well, this is not surprising because the oblique waves talk to each other, they interact non-linearly, and they give actually streaks, okay? So I can break down also the components of the response, and we can see the forcing U, which is an optimal oblique forcing, causes an optimal linear growth of oblique waves. They saturate nonlinear interactions, give rise to vortices, and then to streaks. Okay, all this is great. But now you will ask me the question, how does this converge as I increase the number of harmonics? And actually, when we use only one harmonic, we can see that the convergence of the drag coefficient is quite departed from what seems to be a converged set of curves as a function of amplitude A. But quite nicely, when I increase a lot the number of harmonics and the amplitude, we get a departure from this converged state. And actually, this is where I have the second stage of transition associated with a strict breakdown. So the skin friction coefficient for sufficiently high amplitudes overshoots all the way to the turbulent empirical values. And I want to emphasize that I'm keeping only a few harmonics here. This is a picture as it comes out of the optimization, optimal forcing on the left, optimal response on the right. And we can see these lambda-shaped structures, low-speed streaks actually forming and breaking down. So the forcing amplitude actually has adjusted to trigger also a symmetric here varicose type of streak instability. And if I plot with the Q criterion on top of my low-speed streaks, I can see here the presence of hairpin vortices during this transition to turbulence. This problem was really expensive, and actually what we had to do is I want to emphasize that we imposed reflectional symmetry in the span-wise direction, and later on I will show you results also without the symmetry. Another question that arises is, why do I have to restrict only to one forcing component or one harmonic? And that was to simplify the calculations and the interpretation. So now we can increase the number of harmonic components that we're forcing, so we can have more complicated mechanisms. And actually, now the new mechanism we have, if we have also the second higher harmonics, is like an H-type forcing that leads to streaks exactly in the same way through the amplification of oblique waves. The only difference here is that the oblique waves resonate with the TS waves with a typical H-type mechanism to get a maximum amplification of the oblique waves and subsequently of the streaks and the breakdown. And here I'm breaking down again the components for the forcing. You can see the forcing is a resonant interaction between oblique waves and TS planar waves that give vortices, streaks, and at high amplitudes, the streaks break down in a similar manner like the one we showed earlier. So on the left, I'm summarizing the results that I showed you till now about the optimization, the nonlinear optimization using span-wise reflectional symmetry. If I relax this condition, actually the strict breakdown is completely different, and this is much more efficient than the symmetry condition. So I can go to turbulence, to the turbulent skin friction values much more efficiently at much smaller forcing amplitudes. And now we have seen a completely different change in the streak breakdown. So we have a sinus streak breakdown, quasi-streamwise vortices, which are also associated with a self-sustaining process for invariant configurations. For these two optimal mechanisms, which I call the minimal seed in the frequency domain, I'm plotting also the velocity profile at least 4 stages before the breakdown. So the first stage I plot is the blue curve in a y plus units, and we can see actually we have a Blasius solution at a linear solution, sorry, for the velocity profile. However, as I go downstream, when my streaks are generated and when they break down, actually I depart from this solution. What is really interesting is that only when I have a sinus type of streak breakdown, actually I achieve scaling similar to the ones observed for fully turbulent boundary layers, and we can see a clear, at least for a few, like less than a decade, logarithmic scaling at this stage. So with that, I would like actually to conclude. And I have shown results using the Harmonic-Balanced Navier-Stokes to find what I call the minimal seed in the frequency domain. We have a number of exciting problems and projects running at the moment, extend this methodology to limit cycles, periodic cases, high-speed regimes, And also we start thinking about how we can close these equations using actually data-driven techniques for the closure, but instead of physical space to do actually the closure in the modal space determined by the harmonic-balanced Navier-Stokes equations. And with that, I would like to conclude and take any questions you may have.
Some questions.
Thanks for your talk, George. I enjoyed it.
Thanks, Rick.
Could you go back to the Reynolds number? No, that's it. The one on the right. So if I go along your curves, which are shooting up, there's a sort of a plateau.
There is a tiny plateau there.
What's that?
That I don't know what is happening, but this one coincides with this stage here that I was expecting. Probably one of you people might be able to tell me what it is.
Well, that corresponds to that.
When the streak split there to this lambda type of structure.
Then you get the horizontal bit, but you're not going to shoot up because that's not a temporal plot, is it? Or is it?
So this is an instantaneous plot. So this one should be a period. Actually, this one probably at the first slide. I don't know which case I have. This is a periodic solution, right?
Yeah.
And I plot only one instance. Actually, it's exactly that. So this is how it would look like if you see this video. Okay.
Right.
This is over a period.
I see. So it's not quite. I mean, I would call that transition. Transition, is that transition or not? Is that on the level, not quite there yet?
So in my case, I call it transition because I've reached the empirical skin friction coefficients. And actually, if we look at the energy of the harmonics, this is where I have the explosion of energy to all the harmonics. So I start having a cascade, and that's why I would call this one transition.
So you would actually go right up to the turbulent skin friction. It's just that plateau. I guess I'm confused by why you, or is that just a snapshot actually?
Thank you. So in general, about this oblique wave interaction and also a little bit about the previous talk as well.
Yeah.
I mean, you obtain this behavior by discrete frequencies and discrete betas, which implies an infinitely long coherent time. So I see that this can be obtained and can be obtained in Kashanov experiments using loudspeakers, but how generic do you see this to be? Because with a continuous spectrum, you will not have infinite coherence time, and so the streaks would not grow as much. Can you comment on that?
Yeah, sure. This is a fair point, and that's why these methods are complementary of the time domain methods. So the interpretation of us is that you have continuously supplied disturbances from the environment, that they have a projection on that optimal forcing.
But the coherence time is there.
In a statistical sense, I would expect that there will be some coherence time, of course, because in that case, of course, we should solve the stochastic problem over all the possible frequencies. But this one is, in a statistical sense, the frequency response, the nonlinear frequency response mechanism that we get.
Well, okay, we can.
Yeah.
Okay, one more.
Right. Thanks. That was really very impressive. Can I ask, do you have a a priori or a posteriori way of ascertaining whether your solutions are good? Because you
Yeah, no, that's a really good point. No, this is the answer, because what I told you is I interpolate between linear cases and non-linear fully resolved. The only way I can do is I can start increasing my number of retained harmonics to show convergence. But
can you look at how much is scattering out of your space that you're in? Well, we'll talk later, maybe.
This is a pure spectral approximation.
No, but his truncation, you can look at what your nonlinear term is would be scattering energy out of your space. No, I think it's not.
Okay, I think we continue this in the discussion section. So thank you again.
so much.
But it's still on, even if it doesn't show the